the first 5 chapters that we have in this book are basically some sort of a preparation so that we would know how to deal with the amount of incident energy, how we can consider the amount of energy falling on the absorber of a solar collector, how to calculate the energy which can pass through or partially absorbed by the glass or the glazing, whether it is a single layer or more. And after that, at the end, what we need to look for is how much energy should be uh, received by a solar collector. After that, starting from chapter 6, you can see that we are going to see the kind of direct applications of this collection of information that we're preparing us for the application. That's the solar collectors. So in chapter 6, we are going to be dealing with flat plate collectors, which is what we are going to start or begin with in our next class on next week, inshallah. So we'll be looking basically at chapter 6, which is handling uh, the flat plate collectors, and then followed by the concentrating collectors, and then followed by the energy storage, and so on. And that would probably provide us with an opportunity to assign um, maybe the special kind of assignment or the project of the course, which is related one way or another to the solar collectors and being able to meet a certain load uh, through solar collectors. Say that you need a heating load of a certain quantity that is suitable for either water heating or uh, air conditioning, like heating load in winter to a cold city. Or maybe if some of you are interested, we can exceed that and talk about a condition like air conditioning using the solar energy. If you are interested in that through some sort of an absorption system, that again would be an interesting thing to do. So to complete the picture, we are going to begin with, we are going to recap or start from what we left last time, talking about radiation on sloped surfaces, the isotropic model. That's something is coming from chapter 2, so that's a reminder. And you will see also in the example that we are going to cover today, that we are going through an example that is going to have the information that we have collected in chapters 2, 3, 4, in addition to 5. So this means that what we have been doing over the last few weeks of the course was something like building blocks, like when you buy the Lego and you need to make like a house or a truck or so. What you do is that you bring the pieces of the Lego and you put it together, or like the puzzle that you put the pieces together, so at the end you see a whole picture. So it's just something like we're building upon from chapter to chapter or from week to week. So I've seen this expression for the tilted amount of hourly radiation falling into a surface that has 3 components. One of them is the beam radiation component, and then the diffuse component, the quantity that we have here. Sorry, within between the parentheses is the radiation shape factor from the surface of the collector to the sky. The last term is taking care of the total quantity of the radiation falling onto the surface into the ground reflection, or reflectivity, or reflectance, multiplied by the shape factor between the tilted surface of the collector and the ground. So this is basically some sort of an hourly based energy falling into a surface which is tilted to a certain angle beta. Why we are considering this? Because this is important in estimating the absorbed solar radiation. We have seen this slide last time talking about basically the isotropic diffuse model to calculate S. S is the absorbed radiation of a surface, which is basically the falling radiation into a surface, which is the 3 components of I multiplied by the tau alpha. And we know now how to estimate the value of tau alpha for the 3 components, for the beam radiation, for the diffuse radiation, as well as for the reflected radiation from the ground. Yeah, we talked about the shape factors, whether it is from the surface to the sky or from the ground to the surface. The subscripts, B stands for beam, D stands for diffuse, and G stands for the ground reflected quantity. And there's a certain procedure that we are going to do. We have two alternative ways to reach for this, especially for the components of tau and alpha. So we can either obtain each one of them separately and then combine them, or simply go to a figure that gives me the value of tau alpha or the product right away. This is an example that is considering this quantity to be estimated for an hourly radiation quantity or rate. Here we are talking about a certain specific hour from 11 to 12 a.m. on a clear winter day, where the falling radiation is basically, here the components are given in details, like the total radiation falling at that hour is 1.79 megajoule per meter square. The beam component is 1.38 megajoule per meter square, whereas the diffuse component is 0.41 megajoule per meter square. The three components are needed in the expression for the radiation on the tilted surface. I'll get you back a little bit here and see that we have the I beam component, ID, which is the diffuse component, and the total component I. So all of them are needed, and they are given here in this example. Additional information that are required for completing the problem statement, the ground reflectance is 0.6. And whenever we have the ground reflectance is high, definitely the reflectance definitely would have a value which is from 0 to 1. But when you are seeing values like 0.7 or 0.6 or so, it means that the earth or the ground is covered by ice, snow. For this hour, theta for the beam radiation is 17 degrees. RB is 2.11. A collector with one glass cover having a slope of 60 degrees to the south, it's facing south. The glass has a KL extinction coefficient of 0.037. The absorptance of the plate at normal incidence which is alpha n, is 0.93. Now we are requested to use the isotropic diffuse model, which is given by equation 591, to calculate the absorbed radiation per unit area of the absorber. So we are supposed to be using this equation that you see here, and we need to see how much is the energy absorbed by this collector, by this surface per unit area at this specific hour of the day, which is given between 11 and 12 a.m. Now, there are two approaches for solving this problem. The first one of them, and the two approaches, by the way, are for the determination of the quantity tau alpha. So we can calculate the angular dependence of tau and alpha individually and then combine them together, or we can get the angular dependence of tau alpha right away. We are going to apply both and just see how we can go through for both of them. There's some sort of a standard procedure that we'll have to go here. In the first method, which is determination of the angular dependence of tau and of alpha individually, we first use equation 411.1 to get the angular dependence of alpha, and figure 531 to get the angular dependence of tau. So we're going to obtain this one first and then the second one, alpha and then tau. It's a 60 degrees sloped surface. So the effective angle of incidence that we need for the diffuse component and for the ground reflected radiation is going to be obtained again from figure 541. To explain what I said, these are the two figures. We have 541 and we have 411.1. What we are supposed to do is at 411.1, we need angular dependence of alpha. So from here, to start, now let's look at figure 541. What does it do? It provides us at this slope what is the diffuse or effective angle for the diffuse radiation and the effective angle from the ground reflected radiation. For the diffuse radiation, definitely the slope that we have for the surface is 60. So the effective angle for diffuse radiation only can be obtained from this figure at 60. You construct a vertical line, and here we are going to refer to the dashed line that we have here. This whole thing at the whole lower curve is for diffuse diffuse radiation from the sky. And here you can see the angle can be obtained is 57, whereas the one for the reflected radiation is about 65. This line is not really horizontal, but if you have a horizontal line, it will uh, point to a value of 65. So we have three components here and three effective angles. We are given that the effective angle for diffuse component is 57, which is this line in the middle. You construct a vertical line until it intersects with the curve, and then it will give us the corresponding value of alpha over alpha n, the absorptance divided by the absorptance of the normal radiation falling. And the component which is representing the ground reflected radiation, we can get the value of alpha here, 65. And then you can get the corresponding value of alpha over alpha n. And in the problem, he said that the effective angle for the beam radiation is 17. So from here, you are going to get the corresponding value of alpha over alpha n here. So figure 411 has been utilized to obtain the effective, or basically the ratio between alpha over alpha n for the three components of radiation that we have. Figure 541 has been useful to determine the effective angle corresponding to each one of them. Then, doing that, for the beam radiation, theta is equal to 17. And from 411.1 that we have just looked at now, the value over alpha n has been obtained from the figure as 0.99. What I'm referring to now is this, 17. And the corresponding value here is 0.99, which is what you see here. But this is alpha over alpha n. In the problem, we are given the value of alpha n, which is 0.93. That's given data in the problem statement. So alpha here is going to be the product of the ratio alpha over alpha n multiplied by alpha n. So the value of alpha here for the beam radiation is 0.93. Then we turned into figure 531 to calculate the value of tau. So this is the figure that we're referring to. And remember, here the glass type has been specified to have an extension coefficient into the thickness, which is 0.037. So for the angle of the beam radiation, which is somewhere here, you can get the corresponding value of tau for the condition of a single sheet glass. So from here, the value is 0.88. And this is basically what we have obtained from this figure, from figure 531. It is 0.88 for KL is equal 0.037, and the 0.037 is being stated in the problem. Now we are going to use equation 552 that says that alpha into tau beam component is 1.01 into alpha into tau. And this is basically what we're getting here. So we got tau alpha here for the beam component. Then for the isotropic diffuse component or for diffuse radiation, for an angle of 57, effective angle of 57, we are going to repeat what we have done. Going to equation 411.1, we have seen that alpha over alpha n is 0.94. Tau is equal to 0.83, from which you can get the tau alpha component of the diffuse radiation. It is again repeated for the ground reflected radiation. We have seen that the angle is 65 from figure 541. Then going to 411.1, you can get alpha over alpha n. 531, you can get tau as 0.76, and you can obtain the tau alpha component for the ground reflected radiation. So these three components you can see here have been obtained, and they have been obtained on an individual base. We first got alpha, then we got the value of tau, and then we combine them using equation 552. Then the expression of S by equation 591 is being given here. You can see the components here. And in this figure, we have already obtained the value of tau alpha for the beam radiation, for the diffuse radiation, and for the ground reflected radiation. IB is given to us in the problem. ID is given to us in the problem. RB is also given. I is given, rho is given, and the beta, the angle is 60 degrees. So we can substitute directly here into this equation to calculate the value of S, which is the energy absorbed by this surface at this specific hour and at an angle of inclination of 60 degrees. So this hour, the surface is receiving 2.78 megajoule per meter square. The second method is shorter, because in this method, definitely after obtaining the corresponding effective angles, it is given in the problem for the beam radiation as 17, and then from figure 5.4.1, we could obtain the values of the diffuse component as well as for the ground reflected diffusion. We take these components or these angles, 57 and 65, and initially the value that we have obtained was 14, and then you substitute here to get three values of the ratio tau alpha over tau alpha n right away. And this is basically an equation given for a glass, which is have a refractive index 1.526. But you may recall when we commented on this figure, we said that it's also useful for values of the refractive index of different materials that are close to this value. So from here, we're getting right away the value of tau n of the ratio tau over tau n, which is given as we can see here the effective angle of incidence of the diffuse and ground reflected radiation is 57 and 65. So from figure 531, the value of tau n is 88, alpha n is 0.93, which is given. Accordingly, tau alpha n is given here right away. And the same thing is going to be done for the beam radiation. We have the fraction and we have the tau alpha n, so you can substitute here and obtain it. And the same thing applies here for the diffuse radiation. Now you have the components right away for the beam radiation, for the diffuse radiation, and for the ground reflected radiation. What did you have to do at the beginning? Just obtain the value of tau alpha n, which is this. And after that, the components are obtained. Totally, you are not getting the value of tau alone and alpha alone. We just get it only for the case of the normal radiation, which is used as in these fractions to obtain the value of tau alpha right away. Then we got the values and we complete it like the way that we did. We apply to equation 591 with these three components to calculate the value of S. Now, in this example, we have done both, looked at the value that can be obtained separately or the value that can be obtained collectively for each component of the radiation, the beam radiation, the diffuse radiation, and the ground reflected radiation. But there are even trials to make it simpler in the solution. So in the previous example, each radiation stream on the collector is treated separately. A simplification has been done so that they can be combined together. So by defining an average transmittance absorptance product as a ratio of absorbed solar radiation S to the incident solar radiation IT, so that S over IT is simply tau alpha average. So the average here is taking care of the three components, the beam component, the diffuse component, and the ground reflected component. And here, it would say that if the beam function is high, then this value of the average is going to be close to tau A beam. If the diffuse fraction is high, then the average value is going to be closer to the component tau alpha d. We are going to see then in our next chapter, in chapter 6, that useful energy gain by the collector is usually highest when the beam radiation component is high. As an approximation, the value of tau alpha average could be estimated as 0.96 into tau alpha b. We are going to get back or to refer to this back again when we reach chapter 6, talking about the flat plate collector. And this equation, hence, is providing an easy way, a convenient way to estimate the absorbed solar radiation under these circumstances. You don't have to go through the detailed calculations of different components of S, but you can simply, of each one of these values, but you can simply say that I'm going to get a tau alpha average. If I know the value of IT, I can get the value of S right away. We will see that in chapter 6 anyway, in sections 16 and 17, showing like what's called an incident angle modifier. And this is the one that will enable us to do the simplification of the calculation. The methods for evaluating the long-term solar system, normally, when we are doing a solar collector analysis for heating of a building, like, for example, I need hot water in this house or in this building in general. Sometimes you don't have to do it for every hour and then every day, so that you can get it for the whole year and make sure that your solar collector is doing or is carrying out the required load all over the year. It would be easier to handle it on a monthly basis, so that whatever we have done in the previous example, we need to consider it to be done as average components over a month. And this has been thought of and done by Klein in 1997, where he calculated the monthly average absorbed solar radiation in this manner using many years of data. And he came up with a procedure which appears to be some sort of an acceptable one with good accuracy. He defined a monthly average transmittance absorptance product that can be multiplied by the monthly average radiation incident on a solar collector, which is S, which is HT, and or H on the tilted surface, so that we can get the value of S, which is the average amount of radiation received on a surface on a monthly basis. So the definition is given here is in equation 5.10.1, that alpha T average is equal to S average over HT, where HT, as known, is equal to H multiplied by R. We have seen the values of H calculated alone, terrestrial energy falling on the surface, and R, which is the ratio between terrestrial and extraterrestrial. R actually is given here as HT, sorry, ratio is between HT, which is energy on a tilted surface divided by the total energy falling on a horizontal surface. The expression here is very much the same as equation 591, but there is the only difference here, which is that we are replacing the values of S, H by and tau alpha by the average value, so that you can see the bar over S bar, so it's average, HB, which is average, RB, which is average, HD average, tau alpha average, and so on. For the diffuse and ground reflected terms, alpha tau diffuse, alpha tau grounded, they can be evaluated using the effective angle as we did earlier in figure 5.4.1. We'll see what's the slope of that collector or the surface, and then from there you can get the effective angles for diffuse as well as for ground reflected radiation. And this is all based in equation 219.1, which calculates the value of radiation falling on a tilted surface. So HT is HB average, RB average. This is the beam component, and then HD1 plus cosine beta over 2, that's the diffuse component, and H rho G, reflectance of the ground, 1 minus cosine B over 2, the shape factor, which is the ground reflection component. So this has been considered here using this definition of S is equal to alpha, tau alpha multiplied by h t or h times r, and the value has been obtained here as alpha, as you can see it here. Now, what we are going to do is we are going to use this and estimate the monthly radiation falling into surface. We will see later while we are moving onward on the course, or maybe through the projects, that there is one of the famous methods for calculating the annual requirement of energy of solar energy falling into a solar collector, whatever the type of the collector, to provide a certain amount of energy for a load. And there is a famous method that has been also provided by Klein, which is called the F-chart method. And the F-chart method requires the knowledge of the monthly amount of radiation for the system that you are inspecting or analyzing. So you need it for January, February, March, April, up to December. You collect all of these values and you put it all together so that you can calculate, for example, for these buildings, I'm going to supply, is it 50%, 60%, or even 100% of the energy needed by the solar energy? Meaning that you can have a building where you need hot water, and you said that 50% of the hot water needs are going to be supplied by solar energy, and the other 50% will be by electric heaters, or maybe by a boiler to heat the water and supply it. So that you would know that you are cutting 50% or 40% or whatever from the electric consumption, and you are relying on the solar energy or the renewable energy. Someone else would say, no, I want to make it like 100%. 100%, it means that you will need more collectors. So this kind of analysis is within the F-chart method, and there are even softwares that are doing that. What you see here is the value of the average beam radiation that Klein has proposed for monthly equivalent values. What we see here is part of the figures. The figures actually are given in your book from A to F, which are basically figures A, B, C, D, E, F. 6 figures are there to represent the value of theta B. And what you see here in front of you, figure A to the left, is providing the value of theta B for surfaces that are facing south. You can see at the bottom, gamma is equal to 0. Gamma is equal to 0 here for both of the figures. And for different latitudes, we have it for latitude of 20 degrees north, 30 degrees north, 40 degrees north, and 50 degrees north. And it is given for all the months from January to December. So from here, if you know the tilt angle of your surface, you can get the value of theta B for any month, depending on the latitude. And that made the analysis much easier because you just obtain the theta B simply from this figure. I'm just finding out if you have the books with you, then you can find this information easily on pages 224 and 225, 224 and 225. It has these two figures as figure 5.10.1. What you see here in front of us is A and B, and then the next figures are doing that or showing the same results of theta B for latitudes of 20, 30, 40, 50 degrees north, for gamma is equal to plus or minus 30 or plus or minus 45. So we're talking about a change in the azimuth angle as well for the solar collector. So it's not necessarily due south as you can see here, but this value of gamma can change and the corresponding values of theta can be obtained. These values of theta are evaluating using angular distribution of alpha, tau alpha over tau alpha normal from figure 561. It is showing where Klein has obtained his values, and then Klein and Thielacker equations can also be used to calculate S. So they developed the figures and provided equations for the calculations as well. Each of the R equations that are given in figure in chapter 2, basically 224a and 5a, includes the three terms, which means that the tau alpha beam component, diffuse component, and ground reflected component. And as I mentioned, if the value of the azimuth angle is other than gamma, then the figures are providing us with a way to calculate theta b, and you have also the modified equations 225a that can be used for this case. Let's apply this. This is an interesting sort of a comprehensive example that's going to make us use most of what we have covered earlier in the different chapters. The example is estimate S for a south-facing vertical collector storage, so gamma is equal to 0 here, storage wall at Springfield. We are talking about a vertical collector, so the value of beta is equal to 90. It is south-facing, and it is in Illinois at 40 degrees north latitude. The wall consists of a double glazing, so we're talking about a system with double glazing, with a black finished absorbing surface behind the surface with an alpha normal as 0.9. So alpha normal is provided. The monthly average daily radiation on a horizontal surface H is given in megajoule per square meter in a table, and a table here is following that example that is showing the corresponding values of H for every month. The ground reflectance is assumed to be 0.3. This is rho ground, rho g. The angular dependence of tau alpha for the two cover glazing is shown in figure 561. We have seen that earlier. Figure 561 is giving us the angular dependence of tau alpha. The glass has a KL extinction coefficient into the thickness as 0.0125 per sheet, and alpha n is 0.9. It is repeated again. Calculate the monthly radiation on the wall, HT. So we need to calculate the value of HT. The monthly absorbed radiation S, we need to calculate the value S, and the monthly average tau alpha, and we need to calculate the monthly average value of tau alpha. So that combines most of what we have covered earlier. Let's do it as a step-by-step here. And here the solution, again, it follows some sort of a standard step-by-step procedure to get it done. First thing to do here, that the calculations are going to be done. We are going to start with it here due to the time constraint of the class by doing it for January. And once it's done by January, it would be a very good exercise that you, while you are studying, you can do it for the rest of the months, February, March, April, May, until December. Then you are going to have monthly average values of HT, average values of S, and average values of tau alpha. For these two covers, we are talking about a two-cover system. So we're going to begin with figure 531. At normal incidence, remember, they said here that the angle of incidence is supposed to be 0. Why 0? Because he said that it is a vertical collector setup. Because the collector is vertical, then the angle of incidence is 0. So beta is equal to 90, and the angle of incidence is 0. Now, for these covers, if you start with figure 531, in 531, to remind you again, what you need from this figure is the value of the transmittance. And when we are talking about here at the x-axis, it's talk about the angle of incidence. Remember, it's a vertical surface, and vertical surface means that the angle of incidence is 0. So at 0 value from here, for KL is 0.125, you can get the value. If it's a single cover, then simply you can get the value from here. And that is the first thing that we started with. So Here with absorber normal instance of tau alpha is equal, absorptance is equal to 0.9 for the incident absorbance. Tau n is 1.01 into 0.83 into 0.9. 0.9 is the normal component. Then for the vertical collector of effective incident angle of both the diffuse and ground reflected radiation as 0.95 as 59, which is obtained from figure 541. In figure 541, what we are going to do? We are going to look at a condition at beta equal to 90 and get the values of the effective component of let me get this figure 541. We're going to get the effective incident angle. Look at this. Now we're talking about a slope. It says it's vertical, so the slope is 90. And at 90, both the diffuse component from the sky and the ground reflected component, they meet here at this point. And they meet at this value. When you look at this value, you'll find that this is 55, 56, 57, 58, 59. So the angle here, or the effective angle, is going to be 59 for both, for the diffuse component as well as for the ground reflected component. Both of them are meeting at this point. So from here, the value of theta effective for these two components is the same. Which is the 59. From figure 561, for tau alpha over tau alpha n is 0.83, and this is applied for both of them. So the tau alpha diffuse component is equal to the tau alpha of the ground reflected component, which is 0.83 into 754, and the value here gets as 626. Where did we get that? We get it from figure 561. Going back again to the figure. And we're talking about a value of 59, and from here for a single cover, or it's a double cover this way. For the double cover, you'll get the value of tau alpha over tau alpha n. So from 59, construct a vertical line, and then you can get the value of, it has been shown there as, I guess it was 0.83 or something. So vertical line, intersection, and then you get the value of the ratio tau alpha over tau alpha n. Which is basically 0.83, and you substitute here to get the value of tau alpha d or tau alpha g. So the tau alpha over tau alpha n multiplied by the tau alpha n, you get the value as 0.626. So the value of tau alpha for both diffuse as well as ground reflected value is being given here. Now I need the value of tau alpha for the beam radiation. And for the beam radiation, remember in the previous example, this value was given to us. Now we need to get it, and to get it, we are going to go to the figures that Klein has made. Now, the beta is 90, so for 90, and for a latitude of 40, so we're going to go to this figure, and we are talking about January. This is beta is equal to 90, the last or the second y-axis. For January, this is the value here. So the angle here is somewhere between 35 and 45, and you can just, maybe you can enlarge this figure and make a horizontal line corresponding to the point where January meets the second y-axis corresponding to 90 degrees, and you get the value of theta average B, which is the beam component here, which is given as 41 degrees. Now, doing that, calculating the values of tau B, the values of tau alpha for the beam radiation, tau alpha for the diffuse radiation, as well as for the ground reflected radiation, we have the three components that were needed basically for the H calculation. However, still some information are needed. The value of H that we have on a monthly basis have been given in a table as 6.63. So this is the value of H that is given to us. But to get the value of KT, we need the value of H naught. So for H naught, if you remember, we have table 110.1 or equation 110.1 or figure 110.1. You can use either one of them to get the value of H naught, extraterrestrial radiation in January. The value that is obtained here in the solution of the book is 15.21. When I was checking table 110.1, the value is 15.3. It will not make a big difference in the calculations, but I just wanted to point it out here. So for this value, H naught, and we know the value of H, then KT is basically the ratio between H over H naught. So the value is 0.436. This is going to be used for the mean day of the month. So we need to go back to table 161 to know that if we are talking about January, then the mean day of the month is January 17. This is given in table 161. Then you apply the expression of delta, as delta is equal to 23.45 sine 360 into 284 plus n over 365. I've seen this equation, we used it a lot to get the declination angle as minus 20.9. Substitute in the expression of WS, the sunset angle, which is cosine minus 1 minus tau delta, tan delta into tan phi, then you can get the sunset angle as 71.3. Why are we doing that? Why are we doing this kind of calculations? Because we need to use these expressions that we have obtained in calculating the HD over H, the ratio of HD over H. We need to see how much is the diffuse radiation falling here. And this value is given as a function of KT. And accordingly, the HD over H is 0.458. Then the value of HD, this is the total H that is given to us for January and multiplied by this fraction. So 45.8 of this radiation is diffuse radiation and the rest is beam radiation. So this is the diffuse component. The beam component basically is the 6.63 minus 3.04. You'll get this value of H beam. So now we have the component of H beam and the value of HD, which are needed for the calculation of HT. HT is to be calculated from equation 219.1, which is the one that I'm placing here on the top of the slide. So for this component, we have the values of HB and HD. From equation 219.3, this is why we needed these all angles, the angles that were produced, which are basically the delta and the WS or omega S, were needed to calculate the fraction RB. And the fraction RB has been obtained from equation 219.3 and calculated as a function of these quantities. Just as a reminder, RB is the equation that has cosine phi minus beta into cosine delta into sine omega S plus pi over 180 W omega S sine phi minus beta sine delta divided again on similar parameters of which are functions of phi, delta, and omega S. So from here, the value of RB is to be calculated, which is the second term or the second parameter in the first term of on the right-hand side of this equation. So RB is the one that has pushed us to do the calculations of the angle. In the previous example, 591, these values were given to us. If you remember, it was an hourly basis. So we were provided with the value of IB, ID, and R. Here, they are not given, so we had to calculate them. This is why we had to go back to chapter 2 and come up with these expressions or the values. Having done that already, what we can do then is substitute to get the value of H. Radiation on the tilted surface, isotropic, using the isotropic diffuse model. So it is 3.59, which is representing HB, 2.32, which is representing RB bar, plus 3.04, which is the diffuse component, HD, into the shape factor, 1 plus cosine 90 divided by 2. And then here we have plus the total value of H multiplied by rho ground, reflectivity of the ground into the shape factor. From here, you can calculate the average value of H for the month is 10.84. This average value has been obtained on components of average beam radiation, average diffuse radiation, and average reflected ground radiation for the month of January. Now, having these values, we can substitute into the expression of S, which is the energy absorbed by the surface. The expression of S is given by equation 5.10.2, and I put the equation here and put the calculations in front of it. Again, this is the beam component, this is the R beam, and this is the tau alpha value that we have calculated for the beam component. Then this is the diffuse component, again, H diffuse into tau alpha, diffuse component, into the shape factor. And the third one was H total for January into the ground reflectance into the tau alpha reflected ground component. And you have seen that both of these are equal. You have seen that the effective angle for both of them has met at a value of was it 39 or so, which is basically corresponding to a vertical setup of, or for beta equal to 90. Now the three components of S, energy falling on or absorbed by the surface, 6.03 is the amount absorbed due to beam radiation, 0.95 by diffuse radiation, and 0.62 by the ground reflected radiation. So the total radiation average falling or received on the surface in January is 7.6. So in the example, he wanted us to calculate the value of H, he wanted the value of S, and also he wanted the value of average tau alpha, which by definition, tau alpha is S over HT. S has been calculated, HT has been calculated, so the average tau alpha for the month of January is 0.7. This procedure that we have just gone through now for this example, it is to be repeated again for the rest of the months, and the corresponding values of H are given here. So the first column on this table is the data given, and then based on the different or other data that are given in the example, we can go ahead and do the calculations for the rest of the months: February, March, April, May, and so on. What's going to change as we are going from month to the other? Who can tell me? Let's think about it together. If we are going to move, do we have to repeat everything or not? Any clues? Any answers? If we need to repeat the procedure that we have done, do we have to go to each curve and each value and change them? Or there's something here that can remain as fixed? Are you with me or not? Let's get back to answer this question, get back a little bit. I know it's just, it looks like a lengthy procedure. We'll have to do many things. But when you look at this, there are some of them or some of the data that does not really depend on the day of the month or the month of the year. For example, the values of tau n, the normal value, that does not depend on it. The values that are dependent on the inclination angle, that does not depend on the time. For example, when we are talking about this figure, the figure here is talking about the effective value of theta and providing us with tau alpha over tau alpha n. We use this equation for the determination of the ratio of tau alpha over tau alpha n for case of diffuse as well as ground reflected radiation. It only depends on the number of covers and the angle theta. And then when we go to this figure, we did not need this because we are not going to do the individual calculations of alpha and tau and combine them. We are just going to do it. For this one, this is talking about the slope, and it is providing us with the effective angle for the diffuse component and the ground reflected component. So it seems that the values of tau alpha are not going to be changed from month to month as long as we are talking about the diffuse component and the ground reflected component. But what is going to change? What's going to change basically can be seen from here. As you are going to change from month to the other, the value of theta for the beam radiation component is going to change. So accordingly, the value of tau alpha for the beam component will change. So this is not something that's going to change from month to the other. So that's something that we know. What else? The kind of the calculations of KT, the calculations of WS, this is going to change from one month. Delta is going to change from one month to the other. So the calculations of KT and the calculation of the diffuse component of the total radiation falling is going to change from month to month. So these are values that are going to change. And then you are going to substitute in HT, S, and obtain the average value. So the point that the bottom line here is that you don't have to change all the values or the parameters that you are going to get. As you can see here, what is being changing from one month to the other, tau alpha beam, because this one depends on the figure that we have seen, figure 5.10.1, we have seen that this is a function of the month. Other than that, the values that we have obtained for tau alpha, for the diffuse radiation, for the ground reflected radiation are going to remain the same. Definitely the value of H will change. The value of H naught is going to change, and that's why KT is changing. The diffuse component of the energy is going to change, and because it's a function of the angles, which basically delta and omega S, that are variable from one month to the other. For collectors that are facing the equator, Klein has found that tau alpha beam can be approximated by tau alpha, which is evaluated at incident angle that is occurring 2.5 hours from the solar noon on an average day of the month. What he is trying to do, he's basically trying to come up with a simplification again and again. So what we have here is some sort of a formula that we can apply to calculate this effective angle right away from a formula and or even a figure. So this angle can be calculated from equation 167a or 167b for the southern hemisphere, or obtained from equation 5.10.2. So the equation of 167 here is giving us the value of theta as a function of phi, latitude, beta, inclination angle, delta, declination angle, and beta is the tilt angle or inclination angle. So tilt angle, so that we don't get confused. Delta is the declination angle and omega is the hour angle. So having these, you can calculate the value of cosine theta from. So this rules has been showing acceptable results for the application that Klein has made the approximations for. The approximations were made basically for specific conditions. So for the calculations here are for the determination of tau alpha with a certain angle. This rule leads to acceptable results for solar space heating. So as long as we are talking about solar space heating, then it's fine. If you have a different applications, you cannot use that. For example, you cannot say that I'm going to use that with PV collectors so that I would know what's the value of tau alpha. You don't need that. You cannot do it because the approximation cannot be done for that, and it has not been proved to be applicable for it. So the simplification or the assumption that has been done by Klein here is going to be applied or acceptable for the cases of solar space heating. He also found that the ratio of tau alpha over tau alpha n during winter months is almost constant, and this ratio is about 0.96 for one cover collector. And he said that without the need to go through the figures and the curves to get the value of tau alpha, just calculate tau alpha n normal multiplied by 0.96, and then it will be fine as long as the surfaces are tilted to the equator with a slope change that can be plus or minus 15 for the latitude. For the two cover system, instead of 0.96, you may use 0.94. So what we see here in this slide is basically some sort of trials of getting an approximations that are going to make the solution or the calculations of a similar example to the one that we have seen a bit shorter and easier to carry out. This is a figure that gives the simplifications that he has mentioned. Instead of the different figures that we had earlier, he's proposing another figure where in the x-axis we have phi minus beta. In the y-axis we are going to get the effective beam radiation incident angle, theta beam bar, and the value can be obtained for different months here, as you can see, starting from January to December, for both the cases where phi minus beta is greater than 0 or less than 0. Now we're still with the monthly averaged absorbed radiation, where it is useful to be able to calculate the value of tau alpha bar from tau alpha normal, and the information on this information in figure 561, where tau alpha is simply defined by equation 510(1), which says that tau alpha bar is basically S bar divided by H bar T, which is the radiation falling on a tilted surface. S is the radiation absorbed on that surface. And this ratio basically provides us with the value of tau alpha bar. HT is nothing but the component or the product of H and R. Now, based on that, the expression of tau alpha over tau alpha n can be S over HT into tau alpha n. And then you can get that expression here. We know what's the value of S, and we can use the expression of S. We can divide it by HT, and then you can get this expression here. So for the isotropic model, the value of tau alpha over tau alpha n can be obtained by dividing the expression that we have seen for S previously, which is equation 510(3), we divided by basically the value of HT. And you can see it here. So H bar, HB bar, RB bar divided by HT, and we have the ratio here, tau alpha beam component over tau alpha n, H diffuse component, tau alpha D divided by HT, which is the tilted or overall radiation on a tilted surface, tau alpha n again, and this is the shape factor, and the same thing is being done for the ground reflected value. In this equation, the value of tau alpha bar over tau alpha normal are obtained from equation 561 for the beam component at an effective angle theta b's that can obtain from figure 510(1). And for diffuse and ground reflected components, they are basically obtained at effective angles beta from figure 531. We have gone through that already through the example that we have solved a while ago. Klein and Thielacker equations can be used in similar manner. So the equations of Klein and Thielacker that we have seen in one of the previous slides can also be utilized here. So does this add an additional burden to the steps? Really no, because the kind of steps that we have seen in example 510(1), which is this example, asking us to calculate the value of HT for a certain month, the value of S average for that month and the value of tau alpha average for the month are going to be the same. These are some sort of simplifications if you need to do extensive work and keep on repeating it. But for the sake of analysis, we have a way to do the analysis here, which is by doing the steps or following the steps that we have done in this example one by one. Actually, I was preparing some sort of a similar exercise that we can do for the class today. I'm not sure that we have enough time to do that. It's an exercise basically where you can do the same. You can repeat this. Maybe you can take that while you are studying and consider it. That what if we need to repeat the solution of example 5.10.1? I told you earlier that in this example, we are doing it for the month of January, and you can repeat it for the rest of the months. Even we have looked at what properties, what values can change and what are going to remain constant. But this equation or this example here has been done for, you can see here, estimate S for a south-facing vertical collective storage, Springfield, Illinois, that is consisting of a double glazing. Now, suppose that you may have a quiz that I'm going to ask you, I'll give you exactly the same information here and ask you to do it for a single glazing. One cover, not two covers. And you can do the calculations. The question here would be, I want you to do it in your own and estimate by the end of this calculation, which one of them is higher? Which one of the collectors have received higher rate of energy? Is it the single glazing or the double glazing? Now, without the calculations, who can tell me which one of them is going to result in higher value of S? And this, I'm going to wait until I hear what you think of. For example, if we are talking about a single glass, the components that we see in front of us here, talking about the value of HT, talking about the value of S, and the value of alpha or alpha tau alpha that we have at the end. So we're looking at HT, we're looking at S, and we're looking at tau alpha. And if we're going to repeat the same thing for a single glass, what are your expectations? Or late, for example, for January, the value of HT, will it be the same or it will change? The value of S, will it be the same or change? The value of tau alpha average, will it be the same or change?
Doctor, I think for single, HT will change, will reduce.
What about S?
It will increase.
And tau alpha?
If S increase and H decrease, then it will increase.
Okay, so this is what Abdul Hadi has proposed as an answer to my question. Now, who agrees with that and who disagrees? If you think that what Abdul Hadi said is correct, please just click on the yes mark that you have at the bottom of the names of the participants. And no abstained, which means that you have to say your opinion. Either yes or no. Okay, so far I've just got 1, 2, 3, 4.
Doctor, where can we write it?
You don't have to, you can write it if you like, but it would be quicker if you just clicked or yes or no that we have at the bottom. So what Abdul Hadi is saying, that his expectation is the values of HT will reduce, the values of S will increase, and tau alpha average is going to increase. So I can see from the list here that Yeah, I can see that this is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Doctor, I don't see the, yes,
Do you have the names of the participants showing? If you have the bar, there is participants and it's showing 18. That's your number. If you click on it, it will give you the list of the names. And below the list of the names, you have yes, no, go slower, go faster, more, clear, or like that. Could you see it? Again, move the mouse. And then when you see participants, click on it. And then you can see this additional window that has your names in. Could you see it or not? Yeah, now I see so far 10 of the 18 are approving what Abdelhadi says. Then those who think they are different with him, please now click on the no sign. I mean,
it doesn't appear to me, Doctor. Yes or no?
it does not appear to you. So that's fine. You can just write it to me, or you can just tell me now as you are speaking. What do you think?
I agree.
Fine. Okay. So I saw only one who disagreed, and then probably he changed his mind. So who disagrees can just click on the no or that red circle that you have at the bottom. So, and I said you cannot be abstained. So you have to put your opinion, either agreeing or disagreeing. You cannot just let it go, and then we'll discuss it why. But at least I want to see what do you think when it comes to this. I've seen here 11 yeses, but not a single no. The rest, which means that we have 7, have not yet put their opinions, and I just want to hear it. Even if you are not sure, if you don't know why, just tell us what you think, and then we're going to discuss it so that you would know it after that. Abdurrahim Bima, are you here? Well, let it be a way to check the attendance as well. Abdurrahim? Ammar al-Thumali?
Yes, Abdurrahim, Doctor.
Abdurrahim, okay. So I just want you to put your opinion, Abdurrahim. If we are talking about a single glazing, is it going to be higher or lower? It will remain the same when I'm talking about the values of HT, of S, and of tau alpha. Fahad al-Zahrani? معانا يا فهد?
Yes.
So let me see what you think.
I really don't know.
Just
Which
put it
one?
in. Yes. Omar al-Johani? Do you have Omar?
Yes, doctor.
Yes. Okay. Then Rayan al-Wada'i? Is Rayan with us? Rayan? Maybe he is not. Okay. So Abdurrahim, I still haven't seen what you think. Omar al-Johani, I haven't seen what you think. Abdurrahim Bima, I haven't seen it yet.
I put yes, doctor.
Who?
Umar al-Johani.
Omar Al-Juhani, okay. Which means that I haven't yet heard from Omar. I don't see it, yeah, Omar. I don't see yes or no. So this is, or you are coming, you are logging in with two names, or from your mobile and your computer, or just once?
No, just my computer.
Okay. So Ammar, I haven't heard from you. Abdurrahim Bima did not say, and Ryan Al-Wadai.
It doesn't appear to me, Doctor Ammar Thumar. I don't know why.
It's okay. So you moved your mouse through the whole screen. Sometimes it's on the top, sometimes on the bottom, depending on your own setup. Then you can see that I'm like a menu that has mute or start video or security or participants. Participants is the one that we want. When you click on participants, then you can see this. And then Abdurrahim Bima, I've already got your written. You're written, and Ryan is the one who did not respond to me yet. Anyway, so maybe he's not with us now. So the point here is, let's look at the components that we have calculated. What depends on the month and what does not depend? Now we are talking about whether it is a single surface or double surfaces. What is HT? Abdul Hadi, you are the one who started, so probably I'll get back to you. When we're talking about the value of HT, doesn't it represent the falling energy on a tilted surface?
Yes.
So this is energy falling. We have not talked about the surface anyway so far. We did not talk about it. We're just talking about the amount of radiation falling onto the surface. So whether the surface is a single glazing, double glazing, 3 layers, or even 4 layers, it will not make a difference. Because here we're talking about the energy falling into the surface. But what will be affected is the value of S, because S is the amount of energy absorbed by the surface. So it would make a difference whether the surface is single or double glazing or so. So talking about the value of HT, it will not change if you are talking about different layers on the surface. But what will change is the value of S, and accordingly, the value of tau alpha is going to change. Is that okay?
Yes.
Fine. So which means that for the same month, regardless of the surface covers, the value of radiation falling will not change. It may change from month to month. Yes, definitely, no doubt. It will change if we change the inclination angle, like instead of beta being vertical, if we change it to 60, to 30, whatever, it's going to change. But if we change the covers, the number of covers HT will not change. But what will change? Definitely the value of S will change. And definitely, of course, because of the ratio, the value of alpha tau is going to change as well. So just having a sense of this kind of variations would just, I would believe that it's going to improve our understanding of what's going on here in the calculations that we are doing. It will not be just a set of figures and set of equations that we are applying in, but in every step we would know why are we doing it? What are we doing it for? Like in one of the steps that we're doing here, we had to go back for the information that we covered in chapter 1 and 2 when we're looking for the value of H node, looking for the value of KT and the values of delta and the value of omega. Why did we do that? Because we know that we need this information to estimate the diffuse component over H, which is normally given as a function of KT. And based on that, we would know what is the beam component, what's the diffuse component. We didn't have to do that in example 5.9 because in this example, these quantities were given to us. Here they are not given, so we have to look for them, and this is the way you can get it from the information that you have had earlier. Now we are going to reach for talking about the summary of this chapter. That we have introduced alternative methods to calculate important parameters. One of them is the example we started with today, that the value of tau alpha can be calculated by having tau alone obtained, alpha alone obtained, and then you combine them together with the equation of 1.01 into tau into alpha. Or you can obtain it right away from just a figure by tau alpha over tau alpha n. So you just need to combine them for the normal incidence, and then you can obtain the value of tau alpha, knowing what's tau alpha n right from one figure. We have known how to calculate the radiation absorbed on surfaces that are facing the equator or close to the equator. We have looked at the hourly absorbed radiation. We have looked at the monthly absorbed radiation. All of these are important because this is what we are going to work with when we are talking about flat plate collectors. Part of what we are going to see is how to estimate the energy which is falling, how to estimate the energy which is absorbed. But we are going to go beyond that and talk about how the performance of the solar collector is, how good is it, by defining, for example, the efficiency of the collector. When we are talking about, yeah, something I just, it slipped out of my mind when I was asking you the questions of the values of S. Why does S change? Because S is the absorbed energy by the radiation, by the solar collector or the surface. And then definitely it will depend on, do we have single glazing or double glazing or so on. Your answer that Abdurrahim mentioned, and most of you have agreed with, is the value of S is going to be higher for a single glazing. But we did not say why. Why here? Because the more glazing, the more energy that will be absorbed by the glazing. So that reduces the quantity that's going to reach to the collector, to the absorber surface, which means that less glazing is going to result in higher absorbed radiation. But, and this is what we are going to cover in chapter 6, which is connected to what we covered in chapter 3, which is the revision of heat transfer. What about the losses? Why do we put double covers? Because we need to reduce the convection losses to the surroundings. And that's something that we are going to look at in chapter 6, not only how much energy is falling, but how much energy is being lost and how we can reduce the losses. What we have done here is the isotropic model, but we can also do the HDKR model, which is also useful to do. You will have one example in the book, which is talking about application of HDKR model. I urge you to look at it and read that example. And for surfacing which are facing other than the equator, there is the anisotropic models can be utilized. And for the anisotropic models, you may refer back to chapter 2 into 216 so that it will provide you with information and equations for this model. So that concludes our talk today, and will be